Okay, now we're going to start the unit on torque for my Physics C class. We already talked about torque a little bit. We talked about static equilibrium and Newton's first law. Uh, Equilibrium includes no rotation, which would mean there's no net torque around any axis of rotation. But to go back over it again, turning force happens when there's a line of action for some force that doesn't pass through the axis of rotation. Now, the axis of rotation, it could be fixed, but if it's free to rotate, then inevitably it'll be through the center of mass. You might want to think why that has to be, why through the center of mass. We'll get to that. But a torque is proportional to the magnitude of the force and to the radial distance from the rotational axis, so it's got two variables in defining it instead of just force. So imagine we have a force applied at some point x in an irregularly shaped object. It's horizontal to the right of some magnitude, and it lies along this line of action. So the line of action, it just allows me to talk about some of the freedoms we have in physics problems. This force could be applied anywhere along this line, and at that instant it would have the exact same effect. So it could be applied somewhere on this edge or on that edge or somewhere somehow in the middle. Same effect. All right, the radial distance from the axis of rotation is shown, the red arrow, pointing toward where the force is acting. And the two vectors combine in a cross product, r cross f, vector multiplication, and it results in this third vector torque that's perpendicular to the plane of the two, defined by the two vectors, the radius and force vector. Now the right-hand rule again, the right-hand rule. So you can imagine your fingers are pointing in a direction. The first vector is in the direction your fingers are pointing, which would be the radius vector, which is down to the left, I guess. And then the palm of your hand faces to the lower right-hand side of the screen, which would be the force. So the right-hand rule would be first vector is r, crossing the second vector, and your thumb points in the direction of the resultant vector. So in this case, it'd be coming out of the page. Your thumb is pointing back toward you, back out of the page. That's the resultant vector. All right, so the magnitude though, what defines the magnitude? We talked about this earlier as well. Imagine there's some area in this geometric figure, and the area is defined by what is being swept out when I move the force vector to the tail of the radius vector. So I'm sweeping out some area, and that's equal to the magnitude of the cross product. So we can imagine doing that. Sweeping the force vector to where it's tail to tail, and the result is some area swept out. That angle theta there looks greater than 90. So we can imagine, first, the way we're sweeping r into f, again, defines a positive vector because it points out of the page. Counterclockwise is positive. Sweeping r into f is a counterclockwise rotation. It's easier to visualize when we have the two vectors tail to tail. All right, so the area of this parallelogram, though, is equal to the rectangle defined by the radius vector, the length of the radius vector, and a component of the force vector, f sine theta. So I've defined sine theta to be this interior angle here around this point x where the force is being applied. That angle is actually 180 minus theta, but sine of 180 minus theta is also equal to sine theta. So RF sine theta defines the magnitude of this area. You can imagine I could move the component of that force vector over and redraw the figure as a rectangle, and that rectangle, defined by the length of r and f sine theta, is equal to the area of the parallelogram. I'm sure you understand that. Now it makes sense to consider only the vector component of force that's perpendicular to the radius, since the component parallel, it projects to the center of mass and can only produce translation if the object was not attached at least to a rotational axis. So if this point wasn't fixed, you can imagine this force here has a component that points up and to the right here. So if this object was free to rotate or free to move, then it wouldn't just rotate, it would actually rotate and translate somewhere in this direction at the same time. Some kind of a complicated motion, but it would also move to the upper right. We don't have to worry about that in here. But anyway, we'd have the same area defined if I were to take a component of the radius vector and multiply it by the force vector. Often we do that because what we produce is something called the lever arm, which is often a significant component in a problem. It finds a minimum distance between the line of action and the rotational axis. There are many times where that is the only unique distance defined in a problem, so the lever arm is a fairly important concept. But if I go back for a second, just imagine redrawing it. You see that this line drawn here is also defined by this angle, 180 minus theta, and this vertical component is r sine theta. So both, they're interchangeable, obviously. Typically called the lever arm. All right, now imagine that the component of force that is tangent to the lever arm, we call it tangential acceleration. It causes tangential acceleration. So if the object is rigid, then the sum of the tangential forces times this radial distance from the rotational axis, which again I stated as being the lever arm, produces a net angular acceleration that's inversely proportional to the object's inertia, resistance to rotation. The greater the resistance to rotation, the lower the angular acceleration. So the rotational analog of Newton's second law is in terms of angular acceleration and rotational inertia. So for some particle of mass, you can imagine there's a tangential acceleration equal to r alpha, where alpha is the angular acceleration and the radius, it's magnified by how far we are from the axis of rotation. So the torque is r crossed f, which is equal to r of sine theta, which, as we see, if we replace the tangential component of the force with mass times tangential acceleration and tangential acceleration with r alpha, we end up with the radius twice. Now again, if the object is rigid, then every particle has the same angular acceleration, so we can factor it out. And when we do that and sum up all the individual moments, we've got this term that's being summed times this common angular acceleration. This sum component in here must represent the resistance to rotation. We're defining an analog in terms of Newton's second law, F equals ma. Mass is resistance to acceleration times acceleration, except here now it's angular acceleration, and the term in parentheses represents this resistance to angular acceleration. So we're going to write a capital I to represent that moment. It's called the rotational inertia of an object. So here it is. This is Newton's second law for rotation. The net torque is equal to the sum of all the torques, r crossed f's, and the result is I alpha. The object has an angular acceleration given its resistance to rotation. Okay, well, let's look at applying this. It's obvious from the definition that objects of similar mass but different radial distributions, different shapes, different rotational axes, will have a different resistance to rotation. So typically we have to calculate it, and often given certain assumptions like uniform densities, we can do it by integration. Let's do a simple problem. We've got these four masses spaced apart. They're spaced vertically apart differently than they are horizontally. And I want to define the moment of inertia through some axis that's in the plane of this image here, in the plane of the slide. And what I'm asking here is what position will have the least inertia? So you can imagine I could draw a vertical line somewhere relative to the system of four masses. And I want to know where could I draw it that would result in the least inertia. A simple question. So we're going to let the origin be at the center of the lower left sphere. So the lower left sphere is 0, 0, and the one directly above it is x equals 0 but y equals 2b, and the one to the right is y equals 0 and x equals 2a. So we got to figure out a way of defining a position, and the position x will be somewhere to the right of the lower left sphere, and that would mean that whatever that vertical axis is along that position, it's x away from the origin, but 2a minus x away from the right-hand spheres. All right, so the sum of the moments would be, I've got two spheres at a position x to the left of this axis, so 2 times mx squared represents the moment of the two left-hand spheres, and then 2 times the masses of the two spheres times 2a minus x squared would be the moment defined for the two right-hand spheres. So that would be a simple summation. Now, it should be pretty easily shown that the minimum would be where the axis is drawn right through the center, vertically through the center of this rectangle. Now, how do we prove that? Well, take a derivative of this term, where x is a variable, and set the derivative equal to 0.